So today we will be doing the next part of this lesson. So this lesson is very long. So we will start learning about electric flux and then go to Gauss's law. So my first question is, why do we need Gauss's law? There should be a reason to use this law, right? Can you tell me in the chat, what is the main reason we have a law like this? What is the main use of this? To find what? So I got few answers and all the answers are correct, and the answer that I was hoping for is also there. So you are good. So the main reason we have Gauss's law is to find electric field. So there are other things that we can find using this, but the main thing is electric field. So to find electric field of objects, we use Gauss's law. Now you might wonder, why can't we use this equation? Why can't we just use this? Very good. So the answer is, this equation is only valid for a point charge. But in your lecture, you have seen that you use Gauss's law to find the electric field due to line charges, due to spherical objects, spherical shells. Then what else? Sheet charges, cylinders. You have seen so many examples of charges which are not point charges, right? So we cannot use this equation for anything other than point charge. So we will have to use Gauss's law to figure out the electric field due to charges which are not point charges. So as the first step, let's focus on this term. So this term right here gives you the electric flux, which we symbolize by phi sub E, electric flux. So in Gauss's law, specifically, they are asking you to calculate the electric flux through a closed surface. But as a starting point, we'll first just look at what electric flux is. Okay, then we can go back to Gauss's law and figure out what is meant by a closed surface. So electric flux gives you the electric field lines going through a surface. And like I said before, we symbolize it by phi sub E. So let's take this example first because it's easy. So will the electric flux, or in other words, the number of electric field lines going through this surface, increase with the strength of your electric field? Does it depend on the electric field? So higher the strength of your electric field, more lines will be there, right? We know electric field, when it is stronger, it is represented by more lines. So when E increases, the number of field lines increases too, right? So your flux will increase if your E increase. So flux depends on the electric field. Higher the field, higher the flux. So does it depend on the area? Yes, right? So this, let's say this area is capital A. So the electric flux through the area capital A is bigger than the electric flux through this tiny area, right? So flux is like the number of electric field lines going through a surface. So if your area is small, the number of lines is small, right? Only few lines will go through this. So your electric flux depends on the area as well. So we know that it depends on the electric field and the area. And there's one more thing that we have to look into. And that is the angle between your electric field and your surface. So let's look at this example. I'll call it example 2. So electric flux is the electric field lines going through a surface, right? So your electric field lines should cut the surface. It should go through the surface. What can you say about this example? So we have electric field lines and also we have an area, but does the field lines cut this surface or go through this surface? No, right? It doesn't. So it just goes kind of along it, but it never cuts the surface, right? That means the angle between your electric field and the surface matters. So no matter your electric field is very strong, if this is oriented like this, you will never have flux through it, right? That means the angle between them matters. So I'm going to put a term to represent the angle. I will explain what this theta is. So this equation gives you the electric flux through a surface. And this theta right here is the angle between, so it is very important, it is the angle between the electric field. So this is the electric field. So if we consider this example, electric field lines are going this way. So theta is the angle between the electric field and the perpendicular drawn to your area. So this arrow right here is the perpendicular drawn to your area, right? This is your area. This yellow thing is your surface. And when you draw a perpendicular to that, this is what you get. So the angle theta is the angle between your electric field and this perpendicular. So that is very important, okay? Theta is the angle between E and N cap. So we call this direction, which is the perpendicular, N hat. N hat is the perpendicular direction to the surface or the area. Theta is the angle between E and N hat. So are you okay with this equation? So you know what each term means and you know what theta is. That is the most important thing. So since you know it now, I want you to tell me what theta is in this one, what is theta in this example, and what is theta in this example. What is the theta in, so I got 0 and 90, 0 and 90, so everyone is given 0 and 90. That is correct. So how do we know that? Theta is the angle between the perpendicular, so this is your perpendicular, right? And the electric field. So here, electric field and the perpendicular n hat, E and E are in the same direction, right? Can you see it? This is the perpendicular to your area. That is your n hat, and electric field is also this way. So are they parallel to each other? Yes. When two vectors are parallel, that means theta is 0. So here this is your n hat, right? N hat means the vector or the direction perpendicular to your area. And this is your E field. So E field is this way, your N is this way. They are perpendicular to each other, right? So your theta is 90. So when I substitute in this equation, here phi sub E, I get EA cosine 0. So what is cosine 0? It is 1. That means EA. Here phi sub E is EA cosine 90. Cosine 90 is 0, right? So that is why you did not get any flux from the example 2, because flux electric field lines didn't go through the surface. It didn't cut the surface. So this is the maximum flux you can have when the angle is 0. This is the minimum that you can have, right? No flux cutting through this. So if you have any other angle like this thing, so here the angle between N and E is theta. So any other angle between 0 and 90 will have a electric flux between 0 and EA. So let's do the first problem. Before doing the first problem, I want you to look at this example very carefully. Look at the diagram carefully and tell me what theta is. What is your theta? Yes, it is 30 degrees. It is the angle between electric field and the perpendicular, right? N hat. So this is your N hat and this is your electric field. So your N hat is this way, right? This is your N hat. They have given you the angle between the area and the electric field, but you don't need that. You need this angle. This angle is 30 degrees. So calculate the electric flux, which is given by this equation, and tell me the answer, and make sure to convert these to standard units. The electric field is 150 newtons per coulomb. So I will use the units in this problem so that at the end we will get the units of the electric flux. And the area is 10 into 20, but we will have to convert it into meters, right? So let's start with 10 centimeters. When I convert it into meters, I get 10 into 10 to the negative 2. So in the same way, I have to convert 20. 20, 10 to the negative 2. So meters into meters, we get meter squared. And we have cosine 30. So cosine 30 has no unit. So it is just a number. So when you simplify this, you should get 2.598 Newton meter squared divided by coulombs. But the answer is in 2 sig figs, right? So I'm going to leave it in 2 sig figs, just like you all did. So in the second problem, I let you do it. In the problem, they say the area of one side. So these are the sides of a cube, right? Each side, the area is capital S. And the strength of this electric field is E. So I want you to find the electric flux going through the surface A. And also I want you to find the electric flux going through the surface B in terms of E and S. And once you do that, give me the answer for the net flux going through the whole object, the full object. So A. I think all of you got the answer correct for A, right? So in A, we know phi or the electric flux is given by EA cosine the angle between n hat and the electric field. They are parallel to each other. So your theta is 0. So your answer is, sorry, ES. ES. The area is S here, right? So your answer is ES. The electric flux through B. No flux, right? Through B, because the angle is, this is your new n hat. Angle is 90. Electric field is this way, n hat is this way, so the angle is 90. That means your total flux going through surface B is 0. So now we come to the confusing part or the hard part. So I'm asking you to calculate the net flux through the cube. So when you have a surface, when you are calculating the flux through a closed surface, a cube is a closed thing, right? It's a closed object. We have to consider the direction of your flux. So flux too has a sign. So when we just looked at single surfaces, it didn't matter because it's not object, right? Single surfaces, everything which comes goes out. So we don't care. But in objects, it is different. We consider flux going out. Okay, flux going out of a surface in object, we call it a plus or a positive flux. If flux is coming into a surface, we call it a negative flux. So if it's hard to remember this, you can even think of it as charge. So we know if the charge is positive, electric field lines are going out, right? So plus for out. If it's a negative charge, electric field lines are coming in. So you all have to know this. If the flux is going out of the object, it is a positive flux. If it is coming into the object surface, it is a negative flux. So if we consider the whole cube, we know we don't have any flux from surfaces like B. We already calculated it, right? See, flux through surfaces like B is 0. So this surface are all like surface B, right? Flux, electric field lines don't cut through them. They just pass parallel to those surfaces. So we really don't have to worry about surfaces like B, this, and the surrounding surfaces. But we have to worry about this surface. I call that surface C for now. This surface right here, something the surface opposite to A, this side. So these are the two surfaces that will actually give you some flux, right? Field lines will cut through this surface and come out of this surface. So the net flux will be flux through the surface C plus the total flux through the surface A. Because we do not get any flux from B surface and these surfaces. So are we okay up to this point? Yes. So the next step is figuring out the values. Flux A. Let's look at A. So here the field lines are coming out of this surface, right? If we consider surface A, field lines are coming out. So it is a positive flux from A. And we know the value, it is E times S. The flux through surface A is E times S. Since the field lines are coming out, it is a positive one. So it is plus ES. If we look at surface C, electric field lines are going into the surface, right? It is going in. It is going into the object. So it is a negative flux. So it is negative ES. So when you add the negative ES plus positive ES, you get 0. Yes, so we only have to, so I got a question in the chat. Do we only have to worry about the positive and the negative flux when it is an object, not a single surface? Yes, whenever your surface is a closed surface. So here it is a closed surface, right? Closed means no openings. So this is this is not a closed surface. See, these areas are open. Closed surface is something like a balloon. All the places are closed. So you have to worry about positive, negative when it is a closed surface. So this is Gauss's law, right? So previously I said flux is given by this equation. Are they the same? So is this same as this? Yes. Okay. Sometimes people write E instead of EA cosine theta, they just write perpendicular sine. So it means area, you multiply the area by the perpendicular component of the electric field. So this is the area, this is the perpendicular electric field, right? Sometimes people write it like this. So if you don't like this method, you can always remember this way. Okay, so I like to remember it this way because this is less confusing for me. So what does Gauss say? He says that the total, so we know this is same as flux, electric flux, the total flux through a closed surface is equal to the charge inside that surface divided by epsilon naught. I know it looks confusing, but when we start doing problems, you will see that it is very easy. So first step is, what is a closed surface? So if you want to think of a closed surface, think of a balloon. Okay, so let's think of a balloon. This is a closed surface. So inside this is something closed. So if I ask you to find the flux, net flux through this balloon, you have to look at the charges inside the balloon. You have to look at the charges inside this surface. Let's say we had a plus Q here. So what Gauss says is the electric flux. So this is electric flux, right? I'll use it phi sub E. Phi sub E, or the electric flux going through this closed surface is equal to charge inside it. So we just have one charge. So I'm going to write plus Q divided by this constant. It's easy, right? Although it looked hard, it is not hard. So in some cases, it is not easy to calculate the area, right? So we don't know the area of this balloon, but it is easy for us to get the electric flux going through this balloon just by inspecting the charges, just by looking at the charges. So the important thing is you only look at the charges inside it. Okay, you don't look at charges outside it. So here is another problem, question number 3, and I will do part 1 for you, and you will do the other 2 sections. So I'm going to find the electric flux through the surface S. So through the surface S, we know electric flux, according to Gauss's law, electric flux is equal to enclosed charge. So what is the enclosed charge? Just this one, right? It is a negative charge, so I'm going to write negative Q1 divided by epsilon naught. So I just wrote the electric flux through the surface S. So now I want you to do the flux through the other 2 surfaces. So do it and tell me the answers. Surface, we have this charge and this charge, right? So you have to just add them. So we have a positive Q2 and a negative Q3, right? So you take Q enclosed means you take the total charge inside. Okay, you don't multiply them together. You just take the total charge. That is important. You just take the total charge. What about this surface? There's nothing inside, right? So 0, no charge. So not the absolute value. So here, like I said before, in closed surfaces, we look at the sign, right? We look at the sign. So when we have a negative charge, that means what? Flux is coming into the surface. The net charge is negative. So if we get a positive value, just like in this case, that means your flux is going out. Makes sense, right? So flux has a direction, more like a direction. So negative means coming into the surface. Positive means going out of the surface. So we know, according to Gauss's equation, the flux through a surface, through an enclosed surface like this, is given by the total charge inside it divided by epsilon naught. So what is the total charge? You have 4 microcoulombs, 1 microcoulomb plus 6 microcoulombs. So you get plus 1 microcoulombs. But we need to convert this to coulombs. So make sure you do the conversions. So 1 in 10 to the negative 6 and epsilon is 8.85 10 to the negative 12. So I think you should get the answer as 1.13 10 to the 5. What is the unit? Newtons per coulomb meter squared. So newtons per coulombs is the unit of E, right? This is the unit of area. So that is how I remember it. EA. So in this part, what I'm going to do is, I'm going to explain you or start with the real Gauss's law part. What I mean by real is the main reason why we have this law. So like in the beginning, as you said, we use Gauss's law to find the electric field of objects which are not point charges. So here are a few examples of the things that they will test you in the exam or what is covered in your syllabus. Most important thing is defining your Gaussian surface. So what is a Gaussian surface? So Gauss's law is defined for a closed surface, right? So whatever you are going to do, even before starting the problem, you have to decide what your surface is. Without a surface, you cannot apply this equation. So let's first consider a spherical object. Let's say this thing carries a charge of Q. And I'm asking you to calculate the electric field here. The first step is to draw your Gaussian surface. So Gaussian surface can be any surface as long as it's a closed surface, you're good. So can you draw something like this? Is this valid? This is a surface. Is this valid? Yes, it is valid. But what is the problem with this? It's so hard to get EA, right? So exactly. So it's not symmetrical. So when you calculate E, A cosine theta, imagine how hard it's going to be. Do you know the theta of all the angles? So let's say E, we definitely know E is going like this. It is perpendicular to the surface of the sphere. But here, your n might be like this. You don't know the angle between E and N. And it's going to change at every location. So it's a disaster. So we never, ever choose Gaussian surfaces like this. We always try to select surfaces which are symmetrical. So what is the most symmetrical surface to a spherical object? Another sphere, right? If my Gaussian surface is like this, if my Gaussian surface is like this, what will happen? What can you say about your E and N? Can you see your E and N now always along the same direction? So what is your theta here? Theta is the angle. Theta is always 0. Theta is the angle between E and N, right? See, E and N. E and N are always in the same direction. That means your theta is 0. So instead of EA cosine theta, you can just write EA because it is cosine 0 everywhere, right? Yeah. Okay. So when you select a Gaussian surface which is symmetrical and like this, your life becomes very easy. So now we know the Gaussian surface for a sphere. Let's do an actual problem with the sphere. Next week, we can do problems like this. Okay, these are little advanced than a spherical thing. So I will do this problem with you. Or I can let you do this problem. So I will do the first part. And let you do the second part. Okay, A, B. So first step is to draw a diagram. So they are asking to find the electric field inside and outside. So this should be the other way around. A uniformly charged spherical shell. So spherical shell means you have charge only in this area, right? Because it's a shell. Do we have charge inside? No, because it is a shell, you don't have any charge inside. But we know the total charge is Q and the radius is capital R. So they are asking us to find the electric field inside this shell. So I'll use a different color. So they're asking us to find the electric field at a position like this, right? Inside the shell. So my first step is to draw a Gaussian surface including this location. So my Gaussian surface should be something like this, right? It should be having the radius simple r. So here simple r means somewhere inside capital R. So it should be smaller than capital R, right? It is just a symbol that I introduced to show that it is somewhere inside the spherical shell. So this is your Gaussian surface. So that is your first step. Draw the Gaussian surface. So it is not only on the outside, but it is so since it's a shell, right? Shell means what? Do you have material inside? No, right? So your charge is only on the shell. So only on the shell because you only have material there. It's not really outside, it is like this. Whether it's outside or inside will depend on the type of the shell, whether it's insulating shell or a metal shell. So I just wanted to show that there are no charges here. So we have drawn the Gaussian surface. The next step is Gauss's law. So this is Gauss's law, right? It was something like this. And we know, because this is a spherical object, we have already seen that E, the flux, is given by EA. You remember that, right? We always saw that theta is 0, giving you cosine theta 1. So I'm just going to write EA here. So for all these symmetric objects, you always get EA. You never get EA cosine theta part. We always select the surface so that you always get EA. What is the enclosed charge? Do we have any charge inside? Do we have any charge inside this Gaussian surface? No, right? No. So 0 over epsilon naught. So your electric field inside it is 0. So now I want you to do the same thing for part B. So here also EA is equal to, but now we have an enclosed charge which is Q divided by epsilon. So your electric field, before going to that, we have to figure out what A is. What is A? A is the area of your Gaussian surface. So this is your Gaussian surface, right? So area of a sphere, what is it? 4 pi simple r squared. It is simple r. Why? Because this part right here is about your Gaussian surface. So we need the area of the Gaussian sphere. So E times 4 pi simple r squared is equal to plus Q over epsilon naught. So your electric field is Q divided by 4 pi epsilon naught r squared. And can you see that this is very similar to something that you have seen before? This equation is exactly like the electric field for a point charge, right?